Okay, do we have any questions on the doing probability using combinations? 6. Number 6. Hey, this is the cabin problem. Cabin A holds 5 people and cabin B holds 4 people. If 9 people are randomly assigned to these 2 cabins, what is the probability that Fred and Barney will room together? Let's do the denominator first. This is just like the candy bar problem we had on the test, yeah? Okay, so there's like 9 candy bars or 9 people. How many ways can I pick 5 of them to go into cabin A? I choose 5. And then there's only 4 people left, right? How many ways can I pick 4 of them to go into cabin B? 4 choose 4, right? Which is 1. And it doesn't matter which one you do first. You could have done 9 choose 4 and then 5 choose 5. But then 9 choose 4 is the same as 9 choose 5, so it really doesn't matter which one you do first, yeah? Okay? That's because it's a combination. Now, there are 2 cases. Fred and Barney could be in cabin A, right? Fred and Barney in cabin A, or Fred and Barney in cabin B. Now, if Fred and Barney are in cabin A, how many more people do you need to select? 3, right? So of the remaining 7 people, how many ways can you pick 3 of them to go into cabin A with Fred and Barney? 7 choose 3. And there's only 4 people left, right? How many ways can you put them into cabin B? 4 choose 4, which is 1, but I'm going to write it anyway. Now, what if Fred and Barney are in cabin B? Then 2 more people need to go with them, right? So from the remaining 7 people, how many ways can I pick 2 of them to go with Fred and Barney? 7 choose 2. Got 5 people left. How many ways can I pick 5 of them to go into cabin A? 5 choose 5, which is 1. So you really don't need these because they're just 1, yeah? Right? That's just like the committee problems we used to do before, right? And then what about number 5? And what about number 4? That's like the hardest one in the whole sheet. How come I gotta ask the questions? Just like the last time I only had 1 question, and then the other classes all had like 5 or 6 questions. Wait a minute. So like what about number 3, like the committee with some people on, some people off? You guys can do 3? Okay, number 4. A committee of 4 is randomly chosen from a group of 5 married couples. What is the probability that the committee includes no 2 people who are married to each other? This is kind of like a card problem almost. Okay, let's do the denominator first. What's the denominator going to be? You got 10 total people. How many ways can I pick 4 of them to be on the committee? 10 choose 4. Did everybody at least get the denominator? You don't get any points for that. The numerator is the hard part. Now we want to pick 4 people, but they cannot be married to each other. See, that's the hard part. Okay. So let's say here are the 5 couples. What do you want to call them? The Albertsons, the Botoxes, the Camarillos, the Dumbledores, and the Feds. Okay, so these are got husband and wife from each family, yeah? So if you cannot have a husband or a wife, then what you have to do, don't you have to select like 4 different families then? Okay, so out of these 5 families, how many ways can you select 4 different ones? 5 choose 4. However, okay, then let's say you pick these 4, this one, this one, this one, and that one. But this one has a husband or a wife. You could pick either the husband or the wife, right? So from those 2 people, how many ways can you select one of them? 2 choose 1. And then same thing from this family, right? 2 choose 1. Same thing with them. 2 choose 1. And same thing with them. 2 choose 1. And that's your answer. And then just let the canceling begin after that. Yeah, now it's not that easy. And then number 5. Actually, number 5 is kind of easy. You just gotta read. A quality control inspector randomly inspects 4 microchips in every lot of 100. If one or more, that means at least one, if at least one are defective, the entire lot is rejected. Suppose a lot contains 10 defective microchips and 90 acceptable ones. What is the probability that the lot is rejected? So when is it going to be rejected? When at least one is defective. So we need to find the probability that at least one is defective. But what do we do when we hear the phrase at least one? You do the complement, which is none are defective. That means they're all good. And then you subtract it from 1, right? So what is the probability that if you were randomly pick 4, they're all good? Well, what's the denominator going to be? You have 100 chips. How many different ways can you select 4 of them? 100, choose 4. How many of them are good? 90, and then you're going to select 4. So this would be the probability that they're all good. So what would be the probability that at least one is defective? Well, you just subtract that from 1. Now these numbers are pretty big, so that one you probably want to use a calculator for, yeah? Let me look at the answer. Come on, you don't need a calculator for that. That's less than 1. I remember, was it 2 or 3 years ago, I gave this exact same problem, except instead of 100, I made like 20. So the number is more manageable, yeah. You guys could do that then.
Wait, can we do 2D? Are we done?
I'm done when I tell you I'm done. 2D. 3 cards are randomly drawn from a deck of 52 cards. What's the probability that you get 3 of a kind? Okay, do a specific case, like 3 queens. Okay, queen, queen, queen. Okay, well the denominator is going to be 52, choose 3, right? Because you're picking 3 cards from the deck. Okay, now, what's the probability that you're going to get 3 queens? Well, how many queens are in the deck? 4. How many ways can I pick 3 of them? 4, choose 3. So that's it. This is the probability of getting 3 queens. But what about 3 of anything? Like 3 kings, 3 aces, 3 jacks, 3 tens, 3 nines. So what do I need to multiply by? 13, right? It's got 13 different of these values, right? That's it. Yeah, you can expect 2 or 3 card problems on this test. But like I said, I'm not going to give you a 5 card hand because otherwise the computations are too difficult probably. It's probably going to be a 3 or 4 card hand. Okay, what are we learning today? Okay, now these problems you guys already know how to do, except most books will give you a formula for this. They have a special section on it. But that's okay, we'll do it anyway. It's pretty easy. Okay, suppose you toss, okay, we have a fair coin. Suppose I toss this coin 8 times. Toss a fair coin 8 times. What's the probability of getting 5 tails? So then, of course that means 5 tails and 3 heads, right? Now, we know how to do this already, right? Let's do a specific case. What if you get tail, 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 and then head, 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 like that? What's the probability of that happening? Toss the coin, what's the probability of getting a tail? Half. Another tail. Half. Tail. 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 Head. 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 Is that the answer? No, why not? Because that's not the only way you can get 5 tails, right? So what you gotta do is now you gotta multiply by the number of different orders. How many different orders do you have here? It's like an 8-letter word. How many 8-letter words can you make with 5 T's and 3 H's? 8 factorial over 5 factorial, 3 factorial. But isn't that the same thing as 8 choose 3 or 8 choose 5? Because it's like, out of these 8 positions, how many ways can you pick 5 of them to be the tails? Or out of these 8 positions, how many ways can you pick 3 of them to be the heads? That's why 8 choose 5 and 8 choose 3 are equal. So we already know how to do this problem, but most books, they give you a formula. They call this binomial probability. Now it's up to you whether you want to use the formula or not, because come on, that's easy enough, right? Not the binomial theorem, binomial probability. Now what the heck is binomial probability? Binomial probability is when you do an experiment that only has two possible outcomes, like tossing a coin, either heads or tail, and you do it repeatedly. See, we did it 8 times here. So this is binomial probability, and this is the formula to give you. So let's say P is equal to the probability of a success. Okay, so this is lowercase p, but that's uppercase P. Here, let me make it bigger. Lowercase p is equal to the probability of a success. So like in this problem, what would you define success to be? Getting a tail. Tail is success, head is failure. Okay, now, since there's only 2 possible outcomes, if the probability of a success is P, what is the probability of a failure then? Since there's only 2 possible outcomes. That sounds going to be period P. What's going to happen when we start filming? Get the same look you have now. That's going to be hilarious. If P is the probability of a success, and there's only 2 possible outcomes, what's the probability of a failure? 1 minus P. Oh my goodness. Okay, we're going to define to be N is equal to the number of trials. So in this problem, what is N? How many times am I doing this experiment, which is tossing a coin? 8. So in this problem, N is 8. And we're going to define as R equals the number of successes. So in this problem, what is R? How many successes do I want? 5. I want 5 tails. 5 successes. See, you have to define it. A tail is a success, head is failure. Anyway, whenever I play a tennis match, you flip the racket, I want to say down, which is like tails, whatever. Okay, and in this problem, what is P? What's the probability of tossing a tail? 1/2, and then of course the probability of a failure would be 1 minus 1/2, which is 1/2. Okay, so therefore, once you define these things, the probability of getting N successes is equal. Why don't I just write the formula down? The probability of getting, let's just write it down. N choose R times P to the R, 1 minus P to the N minus R. Huh? It's in the notes. Wait, I didn't put that in the notes. Should be in the notes, but most books will have that. Okay, so here, why don't we apply that? See, you don't really need that formula, just do what you did here, but that's okay, let's do it. Okay, so using that formula, what would it be? A choose 5, because remember, we want 5 successes here. What's the probability of a success? 1/2 to the 5th, and then the probability of a failure is 1/2 to the 8 minus 5, which is 3. That's not 3. Yeah, that's the same thing as this. But then you have a formula to rely on. Okay, let's do another one then. Let's see if you get the hang of this. Binomial probability is an experiment that is done repeatedly, but it only has 2 possible outcomes. Okay, let's say we have an unfair coin now. So let's say you devise a coin that comes up tails like 2/3 of the time. Is it possible to make a coin like that? Yes, you just make it more dense on one side. Speaking of dense. So the probability of a success, okay, so we're going to define a success to be tossing a tail. So the probability of a tail is 2/3, which means of course the probability of getting a head is what? 1/3, okay? I am going to toss this coin, what? How many times? 7 times. What's the probability of getting 5 tails? So let's use the formula that we learned. So what would it be? It would be 7 choose 5 times, now what's the probability of a success? 2/3 to the 5th, and then 1/3 to the 2, because these 2 numbers gotta add up to that, right? 7 minus 5 is 2. Finished. Or you could just do it the way we learned a couple of days ago. How can I get 5 tails? Tails, 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 then head, head. What's the probability of this happening? 2/3, 2/3, 2/3, 2/3, 2/3, and then 1/3, 1/3. But is that the only way you can get 5 tails and 2 heads? No, so how many different orders can you put that in? Well, it's like a 7-letter word. How many 7-letter words can you make with 5 P's and 2 H's? 7 factorial over 5 factorial, 2 factorial. But that's the same thing as 7 choose 5 or 7 choose 2. So it's exactly the same. Okay, now, rolling the die. Now some of you are thinking, how can you roll a die? Got 6 possibilities. You only can use this when you have only 2 possibilities. Well, I'm going to roll a die 5 times. A standard die. What's the probability of getting 3 6s? Well, this is binomial probability because what are we going to define as a success? Rolling a 6, and then the failure would be not rolling a 6, then, right? So what's the probability of rolling a 6? Come on, 1/6. Therefore, the probability of failure would be 5 6 then, right? And of course, this is n, right? And we want 3 successes, so that's r. So using the formula, what is it? 5 choose 3, 1/6 to the 3. This number is over. And then probability of failure to the this over that, which is minus that, which is 2. Now, does this remind you of anything? Or like this one here. Does this remind you of anything? The binomial theorem. This is simply one of the terms in the binomial theorem when you expand what? Let's see if you can put 2 and 2 together.
4.
No, I'm talking about this thing over here. I'll give you a hint. It's the 5th row of Pascal's triangle. Okay, so when you expand a plus b to the 5th, okay, this is one of the terms, but what is a and b? What are we expanding? What are we expanding to get this? 1/6 plus 5/6 to the 5th. That's exactly what we're doing. We're expanding this to the 5th power. Here, let me show you. Okay, using the binomial theorem. Okay, what's the first term going to be? 5 choose
1. 0.
0 or 5 choose 5, right? It doesn't matter. Usually we start with 0, but this one we're going to go backwards. 1/6 to the 5th, 5/6 to the 0, right? What's the next term going to be? 5 choose 4, 1/6 to the 4th, 5/6 to the 1. What's the next term going to be? 5 choose 3, 1/6 to the 3rd, 5/6 to the 2, and so forth. So this thing here is simply that right there. It's just one of the terms. That's why binomial probability is, that's how it relates to the binomial theorem. Anyway, when you do tonight's homework, you don't have to use the formula. You can just do the long way right here. It's the same thing. It's just a more compact way of writing it. Yeah? So tonight's homework is super easy. I don't expect any problems with this. Unless there is, yes.
So all procedures they were binomial go back to binomial theorem.
Yeah, I guess you could say that. Okay, we're done. 7 minutes up. I wanted to pass back all your homework papers. Can I do it in 7 minutes? I don't know if it's got a whole stack here.